In this lecture, we're going to try to understand what it means to diagonalize a matrix and why we might want to do so. And we're going to apply basically everything we've learned about eigenvectors and also change of basis in the previous lecture. So diagonalization is a very useful concept, but it's actually not always possible to diagonalize a matrix. So we're going to talk about, first of all, how to diagonalize a matrix and also when it might be possible. So there's a lot to talk about. So let's get right to it. First of all, you might have guessed diagonalization has to do with diagonal matrices. So let me just remind you what a diagonal matrix is. So diagonal matrix, we've seen some of these. The identity matrix is an example of a diagonal matrix. It's just any matrix, well, I should say a square matrix. We're only dealing with square matrices today. So it's a square matrix with the only non-zero entries are possibly on the diagonal. So it has zero entries everywhere, except the diagonal. I mean, it might have zero entries along the diagonal too, but it cannot have non-zero entries off the diagonal. Okay, so what are examples? Well, here's an example: 3, 4, and then 0, 0. That's a diagonal matrix. But here's another example: 1, 0, 0, 0. Another perfectly good diagonal matrix. Okay, why do we want to talk about diagonal matrices? So yeah, let's get some motivation for this. So why are diagonal matrices so useful in linear algebra? There are many reasons. So let's talk about a few at least. Why are diagonal matrices so useful? So when I see a diagonal matrix, one thing I can do is I can immediately understand the geometric transformation happening. So that's the first thing. So it's easy to understand the geometry. Okay. So for example, let's take this matrix A equals 3, 0, 0, 4, and let's think about the linear transformation associated with this matrix. Well, what is it doing? So let me draw two grids over here really quick. Okay. Well, what it's doing is it's taking 1, 0 to 3, 0, right? And it's taking 0, 1 to 0, 4. Okay. So let me draw out some grid lines just so we can see what's happening. This linear transformation, we can just completely understand what it's doing to the plane. There's nothing unusual going on here. All it's doing is it's stretching this plane by a factor of 3 in the x direction, and then by a factor of 4 in the y direction. So this grid sort of turns into this larger grid. Let me just draw on a few of these, because I don't have that much space anyway. Okay. Right, so again, it's, I should draw on here too. It's just stretching by a factor of 3 this way, and by a factor of 4, so 4x, 3x, that way. Okay. All right, so easy to understand the geometry. That's one nice thing. There are other things that are easy to understand about a diagonal transformation. For example, the determinant. So it's easy to calculate the determinant. The determinant is the area of the unit square under its transformation. So it would just be 3 times 4, which is 12. The determinant is just going to be the product of the diagonal entries. And that's true for any triangular matrix, actually, but in particular, diagonal matrices. What else is it easy to calculate? We can calculate the eigenvectors and eigenvalues. The eigenvectors and the eigenvalues. Right? Because for this matrix, what are the eigenvectors and eigenvalues? Well, we can see them in this picture, right? 1, 0 is an eigenvector with eigenvalue 3, as it gets stretched by a factor of 3, but it ends up pointing the same direction. 0, 1 is an eigenvector with an eigenvalue of 4, because it gets stretched by a factor of 4, and again ends up pointing in the same direction. Okay, and one other thing that you might not have thought of yet, but it's actually easy to do something that we often want to do with a matrix, which is take powers of the matrix. Powers of the matrix. So, why is this a useful thing? Well, taking powers of the matrix is the same thing as, so i.e., we're applying a linear transformation repeatedly. That's all what powers of a matrix means. We often want to do that. Okay, so can we see why it's easy to take powers? So let's say we have a matrix. Well, let's do my same matrix, 3, 0, 0, 4. What if we want to take this to the 100th power? Okay, that seems crazy, but it's not so crazy because see what's. Let me just write out two of them. 3, 0, 0, 4 times 3, 0, 0, 4. You see, when we multiply these two together, we just get, well, yeah, let me write the product of these two down here. We just get 9, okay, 3 squared. But then this entry here is a 0, right? Because we have a mismatch. We have 3 times 0 plus 0 times 4. So we get 0, and then we get another 0 down here, and here we get the 16, which is 4 squared. So it turns out that when you take the power of a diagonal matrix, all that ends up happening is you get another diagonal matrix still, and the entries are just raised to that power. Okay, so we have a really nice formula for taking the powers of a diagonal matrix. We can see this geometrically also, right? Applying this transformation repeatedly, so if we apply it once, we stretch by a factor of 3 this way. If we apply it twice, we stretch that by a factor of 3, so we're at a factor of 9 already. Okay, so we just, yeah. I mean, in general, we have A, B, and this works for larger matrices too, not just 3 by 3. But if we have this matrix to the nth power, that's just A to the n, 0, 0, B to the n. Really nice. On the other hand, what if we had a matrix A, B, C, D, and we want to take that to the nth power? Okay, is there a nice formula for that? Well, almost certainly not. Matrix multiplication is a complicated process, and even if you're just multiplying 3 times, you start getting something very complicated in terms of A, B, C, and D. So there's no obvious formula for powers of a matrix in terms of the entries. But there is a nice formula if it's a diagonal matrix. So that's actually going to be one of the main reasons we're going to care about diagonalization. Okay, so how does diagonalization come up? Well, let me give you sort of the motivating question behind diagonalization. Okay. Let's say we're given a matrix. So given a matrix A, well, let's say an n by n. I want to emphasize that it's a square matrix. So we're only working with square matrices. So given an n by n matrix A, is there a basis such that A, with respect to this basis. Okay, so this is a change of basis from the previous lecture. So make sure you go back and watch that lecture before you see this one. So is there a basis such that A with respect to this basis is a diagonal matrix? Okay, can we find a matrix, a basis that will allow us to express this linear transformation A as just a diagonal matrix? Okay. Let's see an example of this. So first of all, let me just review, what I mean exactly by this. So let's just recall from the previous lecture. What do I mean A with respect to this basis? So recall if we have some non-standard basis, so I called B script in the previous lecture. So V1 up to Vn. This is some non-standard basis, but it is a basis for Rn. Okay. So we're assuming that this spans and is linearly independent. So we can, what we talked about is we could form a matrix U called a change of basis matrix. And how do we form that matrix? We just put the vectors V as the columns. So these are my columns. Make it obvious then. They're the columns. Okay. And so yeah, what is this? Is the change of basis matrix. From what to what? Well, it's a change of basis from B to the standard basis. Then, do you remember how we can convert a matrix A into a matrix with respect to this new basis instead of with respect to the standard basis? So then A with respect to the basis B, script B, is, what do we do? Well, we change the basis from script B to the standard basis. Then we apply the linear transformation given by A. Right? And then we switch back to the basis B. So it's U inverse A, U. Okay. And again, what is our motivating question? So is there a basis, some basis we can choose, such that this U inverse AU, so this is the linear transformation with respect to the basis script B, but can we choose this basis so that this ends up being a diagonal matrix? That would be really nice. I'll show you why that would be really nice. So yeah, is there a basis such that this is diagonal? Here's what I'm imagining, okay? So let's do an example with a matrix we saw before. Let me what this matrix was. It was 6, 5, minus 2, minus 1, okay? And let's just recall this has we should do both of them, vectors and values. So it has eigenvectors 1, 1 with associated eigenvalue 4. Okay, and again, what does this mean? It means that A times this vector v1 is just v1 again, but scaled by 4. Right? So that's my eigenvalue. And my other eigenvector is 2, 5. And it's not just these two, right? Like 2, 2, 3, 3, 4, 4. These are all eigenvectors. But these two eigenvectors form a basis for the corresponding eigenspaces. So this eigenvector has eigenvalue 1. And you can, again, check that by just multiplying this by this matrix. Turns out you just get 2, 5 back again. So that means it's an eigenvector with eigenvalue 1. Doesn't change at all. Okay, so what was our picture here? Our picture was the following. I really just want to emphasize the geometric intuition here, because otherwise you'll just forget about what diagonalization is. a week or two from now. So what's going on? This has these eigenvectors. So here's my first eigenvector. And my second eigenvector is 2, 5. Okay. I'll do it in another color. Okay. Then what happens when I apply the linear transformation T? Again, T is just linear transformation given by multiplication by a matrix A. Well, what happens? This one here gets stretched by a factor of 4, right? So it ends up at 4, 4. Okay. And then the other one just stays where it is. So this is what happens. The question is, can I somehow tweak this? Can I, rotate the axes in a way so that I want to choose my axes so that they align with these eigenvectors here. So in other words, can I somehow view this transformation? It's a little bit weird, right? It's taking this to there and that one staying there. But can I view this as just something in this direction, something in that direction, and I'm stretching by some factor that way, some factor that way. Okay. So in other words, can I view it? Here's how I want to view it. I need another sheet of paper. Yeah. So can I instead view my transformation as I'm going to change basis first. Okay. So I'm going to change basis. And now when I change basis, okay, I'm going to pick that blue vector as one of my basis vectors, and I'm going to pick this purple vector as my other basis vector. Okay? So this is sort of the picture so this is in the basis B. Basis script B. Okay? This is what it looks like in the basis script B. Okay, and then the purple one is going to stay where it is, and then the blue one is going to just get stretched by a factor of 4 again, right? Probably won't be able to change that. But I just sort of want to change the picture. So this is my goal. Okay. Because I can understand this really nicely, and I can do other things like take powers of the new matrix that I get. By the way, what would the matrix look like? It would look like this. 4, 0, 0, 1. But this is with respect to my new basis B, so maybe I'll write a B down there. Okay. Well, what's the idea? I want to choose the eigenvectors as basis elements. Why is that? Because these are ending up pointing in the same direction. Okay. So I'm just going to change basis so that my eigenvectors are the new basis elements. Okay, because then I can get something that will, point in the same direction as before. Okay, if I had chosen some other basis vector or chosen some other vector here as my basis, that might get rotated somehow. And so there's no hope I would be able to view that as just a scaling in one direction, one cardinal direction. Okay, so the main idea is I want to choose the eigenvectors. I want to choose the eigenvectors v1 and v2 to be the new basis. All right, let's see what happens if we do that. Okay, so let's go back to our matrix A. It's this matrix right here. What are my eigenvectors? They're right here, right? So yeah, how should I do this? Well, this is my new transformation. So I'm going to write down my be careful with this. So here's my U, and remember my U is just the basis vectors are the columns, but my basis is the eigenvectors. So I'm going to put 1, 1 in the first column like that, and I'm going to put 2, 5 in the second column. Then I need my matrix A here. Right, so my matrix A is 6, 5, minus 2, minus 1. And then finally here I need to put U inverse. Okay. What is U inverse? Let's do a quick calculation. So it's a 2 by 2 matrix, so inverse is not hard. You just use the formula. And what's the formula? It's dA, so I switch to diagonal. And then this is minus B minus C. Okay, but then, remember, I forgot to do something. Remember what else I have to do? I have to divide by AD minus BC. So I have to have 1 over the determinant. 5 minus 2, which is 3. So that's my inverse matrix. So my matrix U inverse is 1/3 times 5 minus 2 minus 1, 1, if I did that right. And what should this equal? Okay, can you tell me what this is? What this should equal? Well, this, if I chose these to be my basis vectors, right, I can just view this transformation as scaling in the 2 cardinal directions. So this should just be 4, 0, 0, 1. Because again, this is telling me I'm scaling the first basis vector by 4. That's exactly what T is doing. And I'm scaling the second basis vector by 1. Right, so 1, 0 goes to 4, 0, 0, 1 just stays at 0, 1. Okay. But again, this is sort of with respect to my new basis. So that's how I'm thinking of it. And if you multiply these out, you'll see that this is correct. Okay, you should get this matrix. So this is the idea of behind diagonalization. You want to choose a basis so that you can express your linear transformation as a diagonal matrix. Because these are easy to understand. And notice we can write A as, well, let me call this one something. I'll call this, I'll call this capital lambda. Because you see the diagonal entries. What are the diagonal entries? Well, they're just the eigenvalues, right? They're the scale factors. So you see, we can write A as, well, if we multiply by U on the left and U inverse on the right, A is U, sorry, not U inverse, it's just U. A is U times lambda times U inverse, and that's diagonalization. Okay. Notice we need U to be invertible for this all to work out. Okay, so you really need our eigenvectors to form a basis. Okay, because again, the columns of U are the eigenvectors. Let's define what we mean for. I think that's enough motivation. Hopefully you kind of see the idea, but we'll do a bunch more examples. So a matrix, an m by n matrix, capital A, is called diagonalizable. Very important concept. Guarantee you'll see this in whatever you end up doing with linear algebra. Diagonalizable if there exists we're just going to use this example as motivation. So if there exists a diagonal matrix D, okay, D turns out to just be this lambda here, and an invertible matrix, P, such that A is P, D, P inverse. See, so just like that. But I wanted to do this example before I just give you this definition, because if I just say this, you're going to ask me all kinds of questions, like, well, where did this come from, right? why might we want to do this? Well, where did this come from? It came from wanting to change the basis so that we could write our linear transformation as a diagonal matrix. Okay, and that's exactly what we did here. And then we just multiplied through these U and U inverse to the other side, and we got this form. So this is how we define diagonalizable matrix. A is diagonalizable if we can write it as some matrix P times a diagonal matrix D times Not just any matrix, it has to be the inverse of that matrix P that we started with. And the other reason I wanted to do this example is because it basically gives us a recipe for figuring out what P and D are. Okay, this is not some abstract thing. So how do you find P and D? P and D, once we find P, we can find P inverse, right? We just find the inverse of the matrix P. Well, P is a change of basis. It's a change of basis matrix from the basis of eigenvectors. So v1, v2, dot, 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 vn. Okay, so P is a matrix with the eigenvectors of A as the columns. Okay, so these are the eigenvectors of A. And then what is D? D is a matrix where, well, it's a diagonal matrix, so maybe I have to write like this. I have elements in the diagonals. What are those diagonal elements? Well, they're just how much the eigenvectors get scaled by, right? Or in other words, the eigenvalues. So lambda 1, lambda 2, I have to do them in the same order, so be careful there, right? So if I put v1, I need to put lambda 1 there. That's the eigenvalue associated to v1. So it's a lambda such that a v1 equals lambda 1 v1. Now let's go down the diagonal. I have lambda n down here, and because it's a diagonal matrix, everything else is zeros. So that's all there is to it. That's how you diagonalize a matrix. Okay, but that's not quite all there is to it. There's some things that can go wrong. Yeah, what can go wrong here? So, yeah, let's say possible problems. First problem is, if you remember in the eigenvectors lecture, we talked about some situations where we couldn't find any eigenvectors even, or we couldn't find enough of them, essentially. So possible problems, the main problem is what if there aren't enough eigenvectors? I mean, here's one extreme example of that. An extreme example would be this matrix. You can tell this is one of my favorite matrices. It's a 90-degree counterclockwise rotation. The characteristic polynomial, is lambda squared plus 1 equals 0. It doesn't have any real solutions, so there aren't any real eigenvalues. So there aren't any eigenvectors. There aren't any real eigenvectors. So a matrix like this will not be diagonalizable. So we need there to be, first of all, we need the eigenvectors to be real, or the eigenvalues, and that will correspond to real eigenvectors. But we had another problem also, which was, let me actually recall these concepts, because these are a little bit tricky. So remember we had the idea of algebraic multiplicity and geometric multiplicity? So let me remind you what those are. What was the algebraic multiplicity of a eigenvalue? It's the multiplicity. So it's algebraic multiplicity of an eigenvalue. It's just it's the multiplicity of this lambda as a root in a characteristic polynomial. Right, so it's just a power, like if we have lambda minus 1 squared in a characteristic polynomial when we factor it, then lambda equals 1 will be an eigenvalue. The multiplicity will be 2. This is a square. We'll see an example where we have an algebraic multiplicity of 2. But we also had the idea of a geometric multiplicity of an eigenvalue. What was that? Well, remember, to each eigenvalue value, we have a whole space of eigenvectors, and sometimes that space is just one-dimensional, like this example. Right, so for lambda, why did I put lambda 1 equals 1? It should be lambda 2. Right? But yeah, for each lambda, we had a one-dimensional space of eigenvectors. Right? So like in this example, lambda 1 equals 4, and here's my one-dimensional space of eigenvectors, okay, associated with that lambda 1 equals 4, anything along that line. But this 1, 1 is a basis for that space. But there might be a two-dimensional space of eigenvectors associated with a single lambda, and we saw an example of that last time. So what is this technically? I think I defined this already, but I just want to remind you. So it's the dimension of the space of all the eigenvectors associated with that eigenvalue. Yeah. Okay. What is this E lambda? E lambda is just the it's all the eigenvectors. So it's a V such that AV is this lambda times V. So it's all the eigenvectors associated to that lambda, right? Or in other words, yeah, it's a null space of A minus lambda I. Same thing. So that's where we actually like to find the eigenvectors. Okay, so this is what could go wrong. But what could go right? So if the eigenvectors, if we have n of them and they form a basis, right, then we can just do this construction immediately. Okay, so this is the first important fact about diagonalization. This is how we can tell a matrix is diagonalizable. So A is diagonalizable if and only if the eigenvectors of A form a basis for Rn. Right, that's kind of what we saw in the example above. But when is that definitely not going to happen? That's definitely not going to happen if, for example, the geometric multiplicity of an eigenvalue is less than the algebraic multiplicity. So we have a root of order 2. Lambda appears twice, let's say, and the characteristic polynomial is a root, but it only has a one-dimensional space associated to it of eigenvectors. So that's sort of the problem. But what's clear is that if we have let's say we have a two-dimensional space of eigenvectors, we need to choose the columns of this matrix carefully so that we actually have a basis for Rn. Okay, so let's do an example. I think I've said enough. Sorry about all the theory all at once, but yeah, let's do an example that we saw in the previous lecture. So A is going to be the matrix 1, 0, 0. I'm just doing this so I don't have to calculate all the eigenvalues and eigenvectors from scratch. But we haven't diagonalized this yet, certainly. Right. So this is the same matrix I used in the eigenvectors lecture. It's one of them, at least. And remember how we find the eigenvectors. We look at the determinant of A minus lambda I. Okay, well, what is that? Determinant of a triangular matrix. This is not diagonal, right? That one is preventing it from being diagonal. But the determinant of a triangular matrix is still easy. It's just a product of the diagonal entries, right? But it's the determinant of this matrix. So imagine subtracting off lambda from the diagonals. The determinant is 1 minus lambda squared, quantity squared, times 2 minus lambda. And I want to set that equal to 0 and find the roots. And so here are my two eigenvalues, 1 and 2. This has algebraic multiplicity. Again, this is what I mean by algebraic multiplicity. How many times does it appear as a root? right? It's squared, so it has algebraic multiplicity 2, but lambda equals 2 just has algebraic multiplicity 1. Right? Okay, let's try to diagonalize this matrix. So what are we going to do? We're going to find the eigenvectors, and we're hoping that there are 3 eigenvectors. Okay, there might not be though. There might only be 2, in which case we're not going to be able to diagonalize it, because we need the eigenvectors to form a basis. Okay. So we're hoping that the geometric multiplicity, remember geometric multiplicity is always at most algebraic multiplicity. Right? So this one is bigger in general, algebraic multiplicity. But the good situation is when these are equal. Okay? So if we have a root of order 2, we're expecting we want to find a 2-dimensional space of eigenvectors associated with that lambda. Okay? And in fact we do. So I'm just going to recall the calculation that we did already. So for lambda equals 1, we're looking at this matrix, or not this one. We subtract 1 off the diagonal. And we get this matrix. So this is a matrix A minus 1i. And then we look at its null space. And what is that null space? Well, we saw it before. It's just a span of, we can see it now. So what's one thing in a null space? 1, 0, 0. That's a way of combining the columns to get 0. Right? I take 1 in the first column and just ignore the second 2 columns. Thinking of these things as my coefficient of my scalars. Right? And then what's another thing in the null space? I notice that the second and third columns are the same. So I can just take 1 in the second column and minus 1 in the third column. Okay. And again, you can do this the old way too. So what would the old way be? Sometimes you need to do it the calculation way, right? So how would that work? Well, we see what variables are free and which ones are not free. So x1 and x3 are free. I just want to emphasize we're already done just by observing the null space. But if you wanted to do it using a calculation, this is how you would do it, right? And the second line tells me x2 plus x3 is 0. So in other words, x2 is minus x3. So we get this. x1, x2, x3 equals, I'll call x1 s, x3 t, and then x2 is minus t. Forced to do that. And then this is s times 1, 0, 0 plus t times 0 minus 1, 1. Hopefully we got the same answer. So that's the span of these 2 vectors. Well, almost, right? This vector does not look the same as that. Does that mean we did it wrong? Well, no, because the span of that, this is just negative 1 times that, right? So the span of that one and that one is the same as the span of that one and that one. Okay. Okay, great. So, but this is exactly what I was talking about. So this eigenvalue has an algebraic multiplicity of 2. It occurred as a double root. But look at this. I have 2 eigenvectors, 2 linearly independent eigenvectors. So the geometric multiplicity is 2. That's really nice. Right? The geometric multiplicity is 2. So I can use these 2 as 2 of my columns for this matrix P. Right? Great. And so the other good news is that if I look at my other eigenvalue, I'm definitely going to get a third eigenvector from this one. Okay, so this lambda 2, well, let me just skip ahead. So this has an eigenvector, associated eigenvector, as we did this example before. But again, you subtract 2 from the diagonal and look at the null space. It has an associated eigenvector. What was that eigenvector again? It was 0, 1, 0. Okay. Null space of that matrix I was talking about is just the span of this vector. Okay, let's diagonalize A. Here's how I'm going to diagonalize A. Okay. we have 3 linearly independent eigenvectors. I'm gonna have to keep track of the order I write them though. So I'm gonna write these two first. Although you can make a choice here actually. So I'm gonna write should have 1 minus 1, and then I'm gonna write this one. Okay, that was my matrix U. Now I need my diagonal matrix. What's the diagonal matrix going to be? I'm going to put the eigenvalues associated with each eigenvector. But look at this. I have 2 eigenvectors corresponding to 1. So see, I put 2 1s there. This one corresponds to that one, and this one corresponds to that one. And then I need a 2 to correspond to that one. Okay, because this one comes from eigenvalue 2. There's my diagonal matrix. Nice. You see everything is matching up really nicely because I need to put the 1 there twice because it occurred as a double root, but I have 2 eigenvectors. And here, I need to put U inverse. What is U inverse? Can I just see what U inverse is going to be? Well, yeah, you have to calculate U inverse. If I do, remember the idea you write this. This video is already getting pretty long, so I don't want to take too much time here. But you do this kind of thing, and then you put the identity over here, and then you reduce this matrix until the left side becomes the identity matrix, until it's in reduced row echelon form. And then this thing on the right is going to be the inverse. So if I just try to do this really quickly, I think that's going to stay a 1. And then it's going to be a 1, but I'm going to subtract 1. It's supposed to be a 0. That'll be a minus 1. And I have a 1, 1, I think. Sorry, I should have done this ahead of time. But yeah, I believe that's U inverse. Okay, great. Actually, I want to be consistent with the notation. I call it PDP inverse. So, and that's usually the notation used in the literature. Okay, so here's my matrix P. Here's my matrix P inverse, and I've diagonalized A. Very nice. You multiply those 3 together, and you should get A. But this is the diagonalization of A. Okay, I've written it as PDP inverse, the diagonal matrix there. And again, what's the geometric intuition here? It's saying that A, I can somehow view A, if I change the coordinate system, I can view it so that it's just stretching by a factor along the x-axis, the y-axis, and the z-axis. And it's not stretching at all along the x and y-axis, but it's stretching along the z-axis by a factor of 2. Okay. Let's look at an example where you cannot diagonalize a matrix. So here's one of my favorite examples where you cannot do it. It's a 2 by 2 matrix, 1, 1, 0, 1. Okay. Let's look at A minus lambda. We want a determinant of A minus lambda I. Remember, this is a shear matrix. That's what it's doing. It's sort of taking the square and it's sort of shifting it into a parallelogram. But yeah, what's this determinant? It's a determinant of 1 minus lambda, 1, 0, 1 minus lambda. And that is 1 minus lambda squared. That's all, right? So this has a root lambda equals 1. And it has, what would you say about that root? It has algebraic multiplicity too. Right? Okay, let's try to find eigenvectors. So let's look at the null space actually. So we're going to look at the null space of A minus 1 times I, in this case, right? So what is the matrix? Well, I need to subtract the identity from A. So it's a null space of 0, 1, 0, 0. But this null space is only one-dimensional, right? Because this matrix has rank 1. By the rank nullity theorem, rank plus nullity has to equal 2. Okay, so that leaves only one dimension for a null space. And we can say it's a span of, can you see a vector in a null space? Yeah, just take one of the first column and none of the second column. That's the way to get 0. So a null space is just one-dimensional. So it actually has geometric multiplicity. 1. Okay? It's the same eigenvalue, right? Lambda has algebraic multiplicity 2, but only geometric multiplicity 1. So if I try to do the same construction, it's not going to work. I don't have enough eigenvectors. I don't have enough linearly independent eigenvectors to fill up the columns of this matrix P. Okay? And that's because this is only a one-dimensional space. So yes, I could pick 1, 0, and 2, 0, but those would not be a basis. So this P would not be invertible. So this is actually not, A is not diagonalizable. Okay. So let's just recall, what's going on here. So when will a matrix definitely be diagonalizable? So it's diagonalizable if all the geometric multiplicities equal the algebraic multiplicities. And maybe the case I should start out with. So this is actually a useful thing to see right away. So let's say, yeah, I'll do this one first. So if my matrix A has n distinct eigenvalues, say real, right? We're only, yeah. So we want it to have n distinct real eigenvalues. Then each one of those eigenvalues will give me one eigenvector. I'll have n eigenvectors, and they'll be linearly independent. So if A has n distinct real eigenvalues, then certainly we're diagonalizable. So A is definitely diagonalizable. That's a good thing to check just right off the bat, right? So if you have distinct eigenvalues and you have n of them, A is an n by n matrix, then definitely diagonalizable. What if we have fewer than n? Okay, so if n, so if A has, first of all, we need all real eigenvalues to have any hope at being diagonalizable. So if A has all real eigenvalues, but fewer than n of them, distinct values, then what's the deal? Okay. Well, the deal is that A may or may not be diagonalizable. We just saw two examples. Okay. So when is A diagonalizable? So A is diagonalizable exactly when? So I'll just say in this case, A is diagonalizable exactly when? Can you think of what I should write? It's when the geometric multiplicity equals the algebraic multiplicity. For each eigenvalue. Okay. Okay. Great. So that's what we have to check. In this case, we had an algebraic multiplicity of 2, but a geometric multiplicity of 1. That prevented us from diagonalizing. In this case, we only had 2 eigenvalues, right? We were expecting maybe 3, right? Because we have a 3 by 3 matrix. We only had 2 of them. One of them had algebraic multiplicity 2, but thankfully, we were able to find that that lambda actually corresponded to an eigenspace with a basis of 2 eigenvectors. Okay, so dimension of that space is 2, right? That's the dimension of this space of eigenvectors associated with that lambda. And so we were fine. We just put both of those as columns of our matrix P, And then notice in the first two diagonal entries of D, we just put the same eigenvalue 1. Okay, because that was the eigenvalue corresponding to both of those. Okay. Shoot, I shouldn't talk for too much longer. There were a couple other things I wanted to say. I'm planning to make another lecture after this one to sort of explain more about how you use this. This is more just about how to do diagonalization and when can you do diagonalization. Here's a caution. So I don't want you to think that A has to be invertible in order to diagonalize it. So this is a misconception I had for a while too. So A might be diagonalizable even if it's not invertible. Okay, so I'm not going to be able to add something to the unifying theorem in this lecture, because a non-invertible matrix might be diagonalizable, an invertible matrix might be diagonalizable. Can we see an example of a non-invertible matrix that's diagonalizable? Yeah, how about this one? 1, 1, 0, 0. Okay, what's A minus lambda I? It's always what I look at. Yeah, I want to look at a determinant of A minus lambda I to find eigenvalues and eigenvectors. That's determinant of 1 minus 0, 1, 0, and then 0 minus lambda, right? Not 1 minus 0, 1 minus lambda. That determinant is 1 minus lambda times lambda. I guess there's a negative sign. Doesn't really matter, because then I have minus 0, so that's just going to be 0. And so my eigenvalues are lambda equals 1 and lambda equals 0. Well, wait a second. I have two distinct real eigenvalues. So I'm done. A is diagonalizable. Are you convinced? If you're not convinced, here's how we can be convinced, right? So, and let's actually diagonalize A. Okay. So lambda equals 1. That I need to get an eigenvector, right? So A minus 1 times I is what matrix? It's 0, 1, 0, minus 1. Did I do that right? I think so. Right, so the null space of that matrix is what? Well, it's the span of, hopefully you're getting good at seeing these null spaces. Is that what you came up with? Span of 1, 0. Take 1 in the first column, none in the second column. And then for lambda equals 2, or not lambda equals 2, that was my other example. This example actually has lambda equals 0 as an eigenvalue. Remember, if 0 is an eigenvalue, this was part of our unifying theorem. That means the matrix is not invertible. But A minus 0i, that's just the original matrix, which again was, this is good because this had something in its null space. Let's look at a null space of A. That's the span of, can you tell me what the null space of this is? This matrix? 1 minus 1, right? Two columns are the same, so just take one, subtract the other, and that's how I get the 0 vector. So these are my two eigenvalues, or my two eigenvectors, sorry. So here's how I claim I can write A. It's P, D, P inverse, where P is, I put my eigenvectors as columns, 1, 0, 1, 1. But I keep track of what order I did it in. I did that one first and then that one. So I'm going to put 1 there. That's the eigenvalue corresponding to the first eigenvector. And then 0 there. And yes, this is a diagonal matrix, right? We're allowed to have 0 on the diagonal. We just can't have non-zero entries up here and down there. Okay? So this is P, D, and then I need to put P inverse. Let's just take the inverse of this matrix and put it there. Great. There's one other problem I wanted to do. Let me do it really quick. So, and this is going to sound like such a difficult problem, but it's super easy after what we did today. So this problem, let's say we want to find a 3 by 3 matrix. This is going to sound very scary. Find a 3 by 3 matrix A with given eigenvectors. So with eigenvectors, let's say, I can make it as hard as I want almost. 1 minus 1, 1, and let's do 2, 0, 1, and 1, 3, 0. And I'll tell you their corresponding eigenvalues. And I want you to choose a matrix so that they have eigenvalues. Again, I can make it whatever I want. 1 minus 2, 4, let's say. How do we do this? We use diagonalization. Because diagonalization, this PDP inverse turns out not to just be any. These aren't just random matrices. These are related to eigenvectors and eigenvalues. So A is going to be PDP inverse. Okay. I mean, you should check that these actually form a basis, but they do. They're linearly independent. So I'm just going to put those as the columns of my matrix P. I'm writing out PDP inverse. I don't know what A is yet, but I know what P and D are. P is it has my 3 eigenvectors as columns. D has the eigenvalues along the diagonal, 1, minus 2, 4, zeros everywhere else. And then P inverse, well, I don't feel like taking the inverse of this. That's going to take forever. But yeah, you take the inverse of this matrix. That's all you do. Or you get a computer program to do it for you. Take the inverse of that matrix, multiply all 3 of them together. You get a matrix that has these 3 eigenvalues and these corresponding eigenvectors. That's really cool. Okay. In the next lecture, I'm going to talk about a application of this. It's very important, but I'll just highlight that right now. Or just, yeah, I'll introduce this. So this is an immediate application of what we did. It's an immediate application. We're going to be able to take powers of a matrix really quickly, as long as the matrix is diagonalizable. So I just want to give you a hint of the idea before the next lecture. So suppose A is diagonalizable. Then we can write A as P, D, P inverse for some P and some D. Right? In fact, we know how to get that P and D, but yeah, we can write it in that way. Then the powers of A are easy to calculate. So the powers of A are then easy to calculate. And this is so cool. I think you'll like this idea a lot. So why are they easy to calculate? So yeah, why? Well, let's say we want to do A to some power n. Matrix A to some power n. That's just P dP inverse to the power n, which is P dP inverse times P dP inverse times P dP inverse n times. But look at what's happening. Do you see what's going to happen here? Every time we get a P inverse times a P between these 2 factors, that's going to cancel, right? We're going to get one there too. And so that's just going to become the identity. We're just going to be left with P times D times another D times another D n times, and then we'll still have that P inverse at the end, right? Because there was a P inverse there that also got canceled. So let me cross these out. These are getting canceled. So we get this. But that's just P times D to the n times P inverse. See, all the P and P inverses go away except for these 2 at the end. And like we said at the beginning, taking the power of a diagonal matrix is super easy. You just take the powers of the entries along the diagonal. And so I just have to do exactly 2 matrix multiplications in order to take a huge power of a matrix. You know, this could be 10 to the 100 even, this n. It could be something enormous. But it just amounts to doing 2 matrix multiplications if we can diagonalize A. So that's really nifty. And we'll talk more about that in the next lecture.